So good afternoon. Can you hear me and see my screen?
Yes, sir, we can hear you.
Okay. So we'll begin. Um, so before we begin, one small announcement is that assignment 1 will be available at 6:30 p.m. today, and it's due by 9:30 p.m. today itself. So just a quick recap of the topics we looked at the last time. The last time we looked at the definition of the determinant, and we looked at several properties. And today we will continue this discussion on the properties of the determinant, and then we'll move on to discussing about norms. So just to recall, if you take a matrix of size m cross m, the square matrix, then we define the determinant through this cofactor expansion. So we consider the matrix Aij, which is the matrix obtained by deleting the ith row and the jth column of A. This would be an m minus 1 cross m minus 1 square matrix. And we call the determinant of this smaller matrix as the minor associated with the element Aij. And we define Cij to be minus 1 to the I plus j times the determinant of Aij. This is called the cofactor associated with the element Aij. Then the determinant is defined as the summation j going from 1 to m of Aij times Cij, and this can be computed for any I equal to 1, 2, or all the way up to m. And similarly, it can also be computed as the summation I equal to 1 to m of Aij times Cij, and this can be computed for any j 1, 2, or all the way up to m. This is a recursive definition because the determinant of an m by m matrix is defined in terms of Cij, which is a determinant of an m minus 1 by m minus 1 matrix, which will in turn be defined in terms of the determinant of an m minus 2 cross m minus 2 matrix, and so on. And so we need to know what the determinant of a 1 cross 1 matrix is, and that is equal to the element itself. So with this, we know how to calculate the determinant. And the last time we saw several properties of the determinant. So for example, if two rows of the matrix A are equal, then its determinant equals 0. If you subtract a multiple of one row from another row, then that leaves the determinant unchanged. So what this means is that if you do these row reduction operations, that does not change the determinant of a matrix. Also, if A has a row of zeros, then determinant of A equals 0. If A is triangular, then the determinant of A is the product of its diagonal entries, which means that the of a matrix is equal to the product of the pivot elements that appear when you compute the row reduced echelon form of the matrix, with an extra plus or minus 1 depending on how many row exchanges you did in order to compute this row reduced echelon form. If you didn't do any row exchanges, or if you did an even number of row exchanges, then it is plus 1. Otherwise, it's minus 1. If A is a singular matrix, then determinant of A is 0, and if A is non-singular or invertible, then determinant of A is not equal to 0. And the last property where we stopped is that the determinant of the product of two matrices, AB, is the product of the two determinants, determinant of A times the determinant of B. A consequence of this is that if A is invertible, then the determinant of A inverse is 1 over the determinant of A. So are there any questions on this? So we'll continue with the discussion of the properties of the determinant. The next property is that the determinant of the matrix A transpose is equal to the determinant of A. So taking the transpose of a matrix does not change the determinant. So a related interesting question is, what are properties of a matrix that remain unchanged when you take the transpose? So you can see that from this, you can see that the determinant of a matrix is one property of a matrix which remains unchanged by the transposition operation. Similarly, the trace of a matrix is another property that remains unchanged by taking the transpose, because the trace of A transpose is the sum of the diagonal entries, And the transpose operation doesn't change the diagonal entries. It only exchanges the off diagonal entries. And so the trace of A transpose is equal to the trace of A. There are many other properties that remain unchanged by taking the transpose operation, and we'll discuss those more later in the course. Now, how do you show this? So
The rank is also unchanged.
the rank is also a property that remains unchanged by the transpose operation. Okay, we'll later see that the rank is the number of non-zero eigenvalues of a matrix, and so uh, the A and A transpose have the same number of non-zero eigenvalues, and consequently they also have the same number of zero eigenvalues, counting multiplicities. Um, the Another question is whether A and A transpose will have the same eigenvalues. Okay, so that is something we'll see later in the course, and it'll turn out that A and A transpose actually have the same eigenvalues. Now, obviously, if A were a singular matrix, then it means that uh, the rows of A are linearly dependent. So determinant of A is 0. And if the rows of A are linearly dependent, it's a square matrix. So the columns of A will also be linearly dependent. Or in other words, the rows of A transpose would also be linearly dependent. So determinant of A transpose would also be 0. So it is clearly true for the case of singular matrices. Okay, A is singular if and only if A transpose is singular or rank deficient. Um, so we'll consider the non-singular case. So we've seen in the last class that a matrix, any square matrix A, admits a decomposition of the form PA equals LDU, where P is a permutation matrix. L and D are, sorry, L and U are lower and upper triangular matrices with ones on the diagonal, and D is a diagonal matrix. Such a decomposition can be computed for any matrix, and we'll later explicitly study matrix decompositions, where we'll also outline how to compute such decompositions. Yes, question?
Sir, yeah, so is this decomposition unique?
Um, I'm not sure. I'll have to think about it. So it is certainly unique up to a different order of executing the row exchanges in this permutation matrix. But if you do the row exchanges in a different order, I'm not 100% sure if you will get the exact same permutation matrix and the corresponding exact same L matrix. So I'm not sure. I'll have to think about it.
Yeah, okay, sir.
But one thing is that um, you can develop a numerical recipe for computing this decomposition, where there is no ambiguity in the numerical recipe. So yeah, so that much is possible. In other words, when you use that numerical recipe, that will always give you the same P, L, D, and U. So this is true. Okay, you can do this decomposition. You have to take this on faith if you haven't seen decompositions like this. You may have seen decompositions of the form A equal to LU, which is a slightly different decomposition. And this P just accounts for the fact that you may need to do some row exchanges in order to find that decomposition. Okay, so if I take the determinant on both sides of this equation, what I get is determinant of P, because determinant of a product of two matrices is the product of the determinants. The determinant of the left hand side is determinant of P times the determinant of A is equal to the determinant of L times the determinant of D times the determinant of U. Now if I take the transpose of this equation, then that will read as A transpose P transpose is equal to U transpose D transpose L transpose. And so if I take the transpose and then take the determinant, you get determinant of A transpose, determinant of P transpose is equal to determinant of U transpose, determinant of D transpose, determinant of L transpose. And now because L and U are triangular matrices with ones on the diagonal, determinant of L and determinant of U, determinant of U transpose and determinant of L transpose, they're all equal to
One diagonal image.
yes, yes. Um, so also D is diagonal, implies that D is equal to D transpose, so that determinant of D equals the determinant of D transpose. So what we then have is that the right hand sides of the two are actually equal. This is equal to this, and so we have determinant of A transpose determinant of P transpose is equal to determinant of P times the determinant of A. So, but then P is a permutation matrix, and so P is a permutation matrix, which implies that this is true for all permutation matrices. P transpose is equal to the identity matrix. So if you want to see this, I mean, if you think of permutation matrix as performing a row exchange, then P transpose undoes these row exchanges. You can also look up properties of permutation matrices. That's a good exercise to do on its own. But P transpose is equal to the identity matrix. So I have that determinant of P, determinant of P transpose is equal to the determinant of the identity matrix, which is equal to 1, which means that the determinant of P is plus or minus 1. But also, in fact, no, this is in fact a separate point, that for a permutation matrix, the determinant of a permutation matrix is always plus or minus 1. So that means that if the product is 1 and this is plus 1, then this should also be plus 1. And if this is minus 1, then this is also minus 1. So this implies that determinant of P and determinant of P transpose are both +1 or -1. Let me write it a little more clearly. Okay, so because of that, this, if this is +1, this is also +1. If this is -1, then this is also -1, which implies that determinant of A equals the determinant of A transpose. Okay, the next property is what happens to the determinant when you scale a matrix. C times A equals what? How is it related to determinant of A?
C raised to M.
Because every row is getting scaled by C and it is linear in any one of the rows. So you can pull out a C from each row and it becomes C power M times the determinant of A. Another property that you are probably aware of is that the determinant is the product of the diagonal of the eigenvalues of the matrix. So we haven't formally defined eigenvalues yet, but this is a connection that I want to make right now, which we will revisit later. Where lambda I is the ith eigenvalue of A. This also means that we've seen that the determinant of a matrix, the magnitude of the determinant of a matrix is the volume of the parallelepiped formed by the columns of A. And what this means is that the parallelepiped defined by the columns of A can be transformed into a rectangular solid or a cuboid with edges given by of length equal to the eigenvalues of this matrix A. The next property is that if you take any orthonormal matrix.
Sir?
Yeah.
So what is the significance of thinking in terms of volume of parallelepiped?
So that is useful because if you when we it has connections to differential equations and variable transformations. You might recall that when you do a variable transformation, suppose you're trying to find an integral and you do a substitution and you do a variable transformation, then you know that you have to insert what is known as the Jacobian of the transformation in order to change the, so you have some integral f of x dx. If you want to substitute x equal to some g of y, then you can write it as f of g of y times the Jacobian of the transformation x equals g of y times dy. And this Jacobian of the transformation, when it is a linear transformation, so suppose y was equal to ax, then for this linear transformation, the Jacobian of the transformation turns out to be the determinant. And that is related to the fact that if you remember, the point about these variable transformations is if you take a small volume dx and you want to know how that transforms to a small volume dy in the y domain, and that is how this volume of this parallelepiped comes into the picture when you're doing variable transformations. So that is really the connection, at least one connection that I know of, between the volume of the parallelepiped and how one computes integrals involving vectors, vector integrals. So for any orthonormal matrix, the determinant is plus or minus 1. And in particular, a permutation matrix is an orthonormal matrix, and therefore its determinant is also equal to 1 or minus 1.
Excuse me, sir.
Yeah.
Sir, you have written determinant of P or P transpose to be either plus or minus 1.
Yes.
There you didn't use this property, 10th property, right? You just...
Yeah, it is a permutation matrix, which is a special case of an orthonormal matrix. So the property 10 is a more general property. It's true that for any orthonormal matrix, the determinant is either +1 or -1. I think at this point, just
Yeah.
take my word for it that there is no circular argument going on here. That
Okay.
is, if I look at the proving that the determinant of an orthonormal matrix is +1 or -1, I will not be using the fact that um, determinant of A transpose equals the determinant of A. And therefore it becomes a circular argument. To prove this, you use this, and to prove that, you use this, then you've not proved either of them. So that is
Now
not
my
happening.
question is actually, see,
Hmm.
determinant of P, let's say determinant of P is 1.
Hmm.
Does it mean that we are simply making even number of row exchanges for identity matrix? I mean, how are you arriving at the fact that determinant of P is 1 or -1? Is it just the number of row exchanges?
Yes, yes.
Okay.
Yeah,
Okay.
that's all it is.
So by
So
definition, it should follow +or -1, right?
yes,
Because if
yes.
you make
You can
even number of rows, it is
yeah,
okay.
yeah. You can transform P to the identity matrix by performing row exchanges. And if you
Yes.
perform an even number of row exchanges, then the determinant remains unchanged. So the determinant of P is the same as the determinant of the identity matrix, which is equal to 1. If you perform an odd number of row exchanges, then the determinant of P is the same as the determinant of the identity matrix except for a sign change. So determinant of P is -1. Okay.
Yes, sir. Thank you.
Yeah, welcome. The next property is that if B is non-singular, determinant of B inverse AB equals determinant of A. So we've already seen this because determinant of B inverse AB is the determinant of B inverse times determinant of A times the determinant of B. But determinant of B inverse is the same as 1 over the determinant of B. So those two cancel and you're left with determinant of A. This transform, so you take a matrix A and you find a matrix C which is equal to B inverse AB. This is called a similarity transform and it has lots of very nice properties which we will see later. But one thing you can note right away is that the determinant is a property of a matrix which does not change when you apply a similarity transform on the matrix. Of course, another crucial property of the determinant is that it allows you to compute A inverse. So suppose A is a non-singular matrix and suppose we compute this matrix A tilde which is equal to the adjoint of A and defined to be this matrix containing those cofactors C11, C12 up to C1m, Cm1 up to Cmm with a transpose. So this is called the adjoint of a matrix A. Then then we have that if I compute if I take this matrix A tilde and suppose I take its ith row AI tilde transpose, this is the ith row, and I multiply it by AI, you can go back to the definition of the determinant and verify that this is exactly what the determinant's definition is doing. So I'll just scroll up for 1 second to just show you that. You can see that the determinant as defined here is the inner product between two vectors, one vector being the ith column of A and the other vector having these factors Cij, j going from 1 to m. Okay, so if I take the transpose, then that corresponds to picking the ith row of A tilde. So if I do AI, so this is the ith column of A. Then this will be equal to the determinant of A. And it's true for I equal to 1, 2 up to M. And similarly, if I take AI tilde transpose times AJ, what will this be equal to? Any idea?
0.
Why do you say 0?
Sir, I can't give a formal proof, sir.
Yeah. So if you think about it, this AI tilde transpose AJ is actually the determinant of a matrix where you have replaced the ith row of um, A with AJ transpose. So this is a determinant of a matrix whose two rows are actually identical. So this determinant has to be 0. So we see that if I take this matrix A tilde times A, then this is equal to uh, the diagonal entries of this product are all equal to the determinant of A. All the off diagonal entries of this product are equal to 0. So this is equal to determinant of A times the identity matrix, which means that A inverse is equal to 1 over the determinant of A times A tilde. So the determinant allows you to find the inverse of a matrix. Although this is typically not the way you want to compute the inverse of a matrix. So for instance, if you're using MATLAB, this is not how MATLAB would compute the inverse of a matrix, but it gives us a formula or at least one way to try to find the inverse of a matrix. So those are some of the properties of the determinant that I wanted to discuss. Um, Before I move on to norms, maybe very briefly I'll talk about a few uses of the determinant. The first is that it can be used to test invertibility. Okay, if determinant of A is 0, then the matrix is not invertible. If it's non-zero, then it is invertible. The second is that if you consider the family of matrices, A minus lambda I. Now this is a family of matrices because lambda can be anything. So let me just say it's any complex number for now. So as I vary lambda over the complex plane, I'll get different matrices. And I look for what values of lambda will make this A minus lambda I a singular matrix. So I look for solutions to determinant of A minus lambda I equal to 0. Now if I expand this out, this will turn out to be a polynomial of degree n, which means that it has exactly n roots. Counting repetitions. And therefore, there are exactly n values of lambda which will make this determinant equal to 0. For any other value of lambda in the entire complex plane, this determinant will be non-zero, or A minus lambda I will be a non-singular matrix. And these n roots give us the n eigenvalues. So determinant is also something that helps us in computing the eigenvalues of a matrix. The other uses are that I already mentioned that determinant gives us the volume of the magnitude of the determinant is the volume of the parallelepiped formed by the columns of A. The next one is that the determinant can actually be used to obtain a formula for each pivot element in the row reduced echelon form. I'll discuss this more later when we talk about matrix factorization. But for now, for the sake of completeness, I'll put down this thing. Gives a formula for each pivot element in the row reduced echelon form. And finally, but not the least for sure, is that the determinant gives us a measure for the sensitivity of a solution to y equal to ax to changes in y or a. So specifically, if you're given a set of linear equations y equal to ax and you're asked to find x, and suppose tomorrow somebody came back to you and said that y was measured incorrectly, and so there is a small perturbation, and the actual y is some y prime, then you've already given them your solution. Then you can compute how sensitive your solution is to this error in y. Similarly, if they said that the a that was used to obtain y was not a but instead it was a prime, then you can actually compute how sensitive the solution is to this perturbation in the matrix A. So this is another sort of chapter by itself, and again we will study this later in the course. So are there any questions?
Sir, can you please explain the point 4 once?
So for now, I just want to say that when you do this, when you find this row reduced echelon form, you will obtain these pivot elements, and then you'll have some things in the upper triangular part, right? And the determinant uh, can be used to obtain a formula for what each of those pivot elements will be. When we look at decompositions, we'll study this connection.
Okay, sir.
But right now, I just want to say that determinant is also related to matrix factorization,
Okay, sir.
or trying to find this row reduced echelon form. So now we move on to discussing about norms. This is chapter 5 in the textbook. So I can say that probably whatever we discussed so far is loosely things you've already seen before. There's probably not too much new material that you have never heard of that I've covered so far. But from now on, hopefully you'll get to see some new things when we discuss these norms and its properties. So what is the norm? What is a norm? A norm is simply a way to measure length. So we've already seen the Euclidean norm. Which is given by, if I take a vector z, then z transpose z, which is equal to summation I equal to 1 to n zi square. Okay, here it's implicitly assuming it's a real vector, so the mod is not required. So let me not confuse you. I'll remove the mod here. Okay, this is one way to measure the size of a matrix, of a vector. And I think the last time I alluded to this, but there is a, for example, a simple generalization is I could define, I'll just write a subscript a here, and I can define the measure of a length to be equal to summation I equal to 1 to n ai times zi squared, where ai's are some numbers greater than 0 for I equal to 1 to n. So we'll see that in just a few minutes, we'll see that this is also a valid definition of the norm of a vector. And a question that we'll answer is that are there other generalizations? And also, how does one extend this to somehow measure the size of a matrix?
So what is A?
A is some number. AIs are numbers. And A is a vector with A1 to AN along. It is an n-dimensional vector.
Okay, sir. Okay.
So in general, we humans are very fond of associating numbers with everything. And so that once you associate a number with things, you can even think about rank ordering things based on that number that you're associating with each of these quantities. And so perhaps, that could be one way to think about why we are interested in norms, is because it allows us to associate a number with different things. So let me formally define a norm. So let V be a vector space over a field F. So for the purposes of this course, think of it as either the real line or the complex plane. Then a function F, or not F, we'll define it this way, which maps from the vector space V to the real line, is a vector norm if for all x, y belonging to this vector space V, it is true that the norm of x is greater than or equal to 0. Norm of x, actually I'll call this 1a. If and only if x equals 0. 2 c times x norm is equal to mod c times the norm of x for every c belonging to f. And the last one is the triangle inequality, norm of x plus y. This is the only place where y enters into the picture. So this is called, this property is called the non-negativity property. And this property is called the positivity property. This property is called the homogeneity property. And this is the triangle inequality. Now, couple of variations are that if the property 1a is not satisfied, then it is called a semi-norm. And if the triangle inequality is not satisfied, then it is called a prenorm. So we'll refer to some of these later when we want to state certain properties. So for some properties, it's enough if the norm that we are considering is a prenorm. For some other properties, it's enough if it's a semi-norm, but for others, it needs to be a norm. So these are the four things that a function which maps a point in the vector space to the real line needs to satisfy for it to be considered a norm. So essentially it's mapping to R plus, the positive half of the real line. So any questions about the definition? Because now we are going to discuss several properties of norms. So the first property is that if is a vector norm, then norm x minus norm y in magnitude is less than or equal to the norm of x minus y for every x, y in V. You can see that this is very similar to a triangle inequality. So if I just want to illustrate this by a picture in 2 dimensions, then if I have a vector x and another vector y, then x minus y is actually this vector. So let's change color. This is x minus y. Then what it's saying is that the length of this vector is more than the difference between these two lengths. So how do we show this? It's very simple. So what we do is we take y and we can write y to be equal to x plus y minus x. So this means that if I take the norm of y, if I take the norm both sides and then I apply triangle inequality, this is less than or equal to the norm of x plus the norm of y minus x. So this means that if I take norm y minus norm x, that is less than or equal to the norm of y minus x, which is equal to the norm of x minus y, because scaling by minus 1 will only scale the norm by the magnitude of minus 1, which is equal to 1. And similarly, similarly you can exchange x and y, and or you can write x to be equal to y plus x minus y. This exchanges x and y here, and that will give you that norm x minus norm y is less than or equal to norm of x minus y. So you see that this and this both are actually less than x minus y, which can be compactly written as norm x minus norm y is less than or equal to norm of x minus y. Okay, um, so earlier we looked at this thing called the usual inner product or the dot product, where xy was defined to be y transpose x or y Hermitian x for the complex case. So this is I mentioned several times that this is a special case of a definition of an inner product. The more general definition is like this. So let V be a vector space over F. Then this dot comma dot bracket, which maps from the Cartesian product of V with itself to the field F, is an inner product if for every x, y, and z belonging to this vector space V, it is true that the inner product of x with itself is greater than or equal to 0, which is the same as our non-negativity. And second, which again I'll call 1a, x equals 0 if and only if x equals 0, which is the positivity property. Linear in the first argument, x plus y z equals xz plus yz. This is also called the additivity property. And then there is a homogeneity property, Cx y equals Cxy. And the fourth property is that xy is the complex conjugate of yx. So if you exchange the arguments, then what you get is the complex conjugate of the inner product. So this is the formal definition of an inner product. Any function that maps v cross v to f is an inner product if it satisfies these 5 properties.
Sir?
Yeah.
So why in the definition, why is it V cross V?
Because it's taking 2 vectors in V as its input argument. So it's the Cartesian product of V with itself.
But both the vectors are in V itself, right?
Yeah, they need not be the same vector though. It's x and y in V. So you can take any vector in V and any other vector in V and ask what is their inner product. So the set of all possible, so just for understanding, if you think of V as consisting of a finite number of vectors, say k vectors, then when you're taking inner product, there are k squared possible inner products you can compute. Take the first vector as the first argument and the first vector as the second argument, or first vector as the first argument, second vector as the second argument, and so on, and up to the vth vector and the vth vector, v comma vth vector, k comma kth vector.
Sir, my doubt was that for if we denote a function, it's like domain to range, but the domain for both the inputs is v only. So why is it v cross v?
No, that is how it is defined. The domain is v cross v. The domain is not v. You are allowed to pick two vectors from v. When you're allowed to pick two vectors, it's like you're picking picking the input, or the domain is a pair of vectors from v. That is denoted as the Cartesian product of v with itself. So for
Okay.
example, when I define a norm, it's a mapping from v to f, because there's only one input vector that I need to calculate the norm. Here I have to take two vectors.
Okay, sir. Thank you, sir.
Yeah. Just think about it for a minute. It'll be clear to you. Okay, so now the reason why I brought up
Excuse me,
this
sir.
inner product. Yeah.
Sir, these two vectors can be from different subspaces, right?
No. So here it's defined for a vector space. So
Sir, like how we check orthogonal complement subspaces, for that we use inner product is equal to 0, right?
right. So
And yeah.
there you are actually defining an inner product over, for example, if you take two subspaces of R to the M, you are saying that these are vectors in subspaces of R to the M. And then you're defining an inner product over R to the M. So it's valid to think about what is the inner product between any two vectors in R to the M.
Yeah, that's what I was asking. Means they can be different subspaces of V, vector space.
The inner product is defined between any two vectors in V. And
Yeah.
yes, of
Yeah.
course, that
Yeah.
means it is defined between two different subspaces of V as well.
Yes. Thank you.
Okay, so the reason why I brought up the definition of the inner product is because there's a close connection between inner products and norms. And uh, here's the lemma that makes this connection. If is a vector inner product on V, on a vector space V, then the square root of the inner product of x with itself for any x is a vector norm on V. So this means that if I define this to be a vector norm where the inner product has these four properties, then I can show that this notion of a vector norm satisfies the four properties I need in order to define a vector norm, and therefore it is a valid vector norm. I won't prove this here, so I'll leave it for you to look up in the text, but it's a straightforward proof. The proof, essentially, the only idea that the proof uses is the Cauchy-Schwarz inequality, mainly to show this triangle, that the triangle inequality holds. The other properties are trivial from the fact that this is a inner product and it comes from here itself. But you need you need to show the triangle inequality, for which you need the Cauchy-Schwarz inequality. One other thing is that a norm derived from, so when we define a norm in this way, we say that such a norm is derived from an inner product. And a norm derived from an inner product, it satisfies what is called the parallelogram law, which norms that are not derived from an inner product, we'll see examples of that momentarily, they don't need to satisfy this. So the parallelogram law is that u plus v, if u and v are two vectors, then this norm squared plus norm of u minus v squared is equal to 2 times the norm of u squared plus the norm of v squared for every u v belonging to this vector space V. So if you think of this as the inner product square, you can see that when I take the inner product of u plus v with itself, I'll get the inner product of u with itself plus the inner product of v with itself plus 2 times the inner product of u with v. When I take the inner product of u minus v with itself, I'll get the norm of u square plus the norm of v squared minus 2 times the inner product between u and v. That is for the real case. For the complex case, you will get something like uh, um, u Hermitian v plus v Hermitian u, but you will get exactly the negative of that out here. So those two will cancel. And so all you're left with is 2 times norm u squared plus norm v squared. So if it's derived from an inner product, it's easy to see that the norm satisfies this parallelogram law. And it's called the parallelogram law because these two terms are, if I construct a parallelogram from with u and v as the sides, then if I complete this parallelogram, then this vector is u plus v, and this vector is u minus v. And so what it's saying is that the lengths of the diagonals of the parallelogram squared, if you add them up, that is equal to 2 times the lengths of the sides squared, the sum of the lengths of the sides. So this part is lengths squared of diagonals, and this part is of the sides. Okay, so now the next thing I want to talk about is various examples of vector norms. Since we are like really at the last tail end of the class, I'll stop here and continue with this in the next class. Are there any questions?
Sir, this vector norm and inner product, the relation holds for any norm? I mean, we have defined one norm, two norm previously, so it's
So some of those norms are derived from inner products. In fact, in the next class, we will see that if I define the L1 norm, now this is not derived from an inner product. So it satisfies all the properties of a norm, but it doesn't come, you cannot write this as under some definition of an inner product. I cannot write this as for some definition of an inner product. I cannot write it like this. So there are norms which are not derived from inner products. There are norms that are derived from inner products.
Okay, sir.